In this section, we talk about analyzing graphs. Graphing functions can be easily done by technology, but we must use calculus to understand what we are seeing. Now, if we have a graph, if we already have a graph graphed by a technology, by computer or by graphing calculator, then we need to know some properties or features of graph to get better understanding of the meaning of that curve or graph. Or if we want to graph a function, then we need to focus on some features of that graph. And if we know these features or properties or elements, then we can graph or sketch a graph nicely and easily and accurately. So what are the features of a graph? We have some features here, 5, 6 or so, but the most important ones are the following. First, we need to determine the x and y intercepts. What do we mean by x-intercept? X-intercept means to put or where the graph intersects the x-axis. And in order to find that point, we need to set y equal to 0 and then solve for x. If we want to find y-intercept, then set x equals 0 and solve for y. Now the second feature is the extrema. We studied extrema in this chapter, and that means to determine the max and the min of the graph. The maximum point and the minimum point, or the maximum value and the minimum value. 3 points of inflection, and these are applications of the second derivative, points of inflection. And the importance of this is that the point of inflection is the point where the graph changes its direction, its concavity. So we know we can if we determine this point, we can determine the point where the function changes the concavity. For example, if it was concave up, then it changed the concavity to be concave down, or vice versa. So this is a very important point in given a graph or in graphing some functions. 4, we need to focus on behavior near singular points. Singular points of the function. And here, if the singular point is x equals c, then we need to study. We can't determine the value of the function at that point, because the derivative at the singular point does not exist. And in order to graph that function, or to know the behavior of the function around the singular values, I mean the values where the function is not defined, we need to study the limit of the function as x goes to this point, this singular point from the right, and find the limit as x goes to this point from the left. So for example, if we have this graph of a function, we notice that on the y-axis, the function at x equals 0, I mean c equals 0, the function is not defined on the y-axis. So in order to study the behavior of the function near this singular point, we need to take the limit from the right, and then we find that the limit is negative infinity, and then the limit from the left, and we find that the limit is plus infinity. So that gives us good information about the behavior of the function near the singular point. 5. We need to determine the behavior at infinity, and this is sometimes called end behavior. So if we have a graph like this, as we can see, as x approaches infinity from the right, the graph approaches 0. The height of the function approaches 0. And as x approaches negative infinity, the graph of the function approaches 0. The height of the function approaches 0. So that gives us some indication about the behavior of the function as at the end behavior of the function. As x goes to plus infinity or negative infinity, what happens to the function or to the curve of the function? So if we focus on these things, let me write this mathematically. The number 5, we need to find limit of the function as x goes to plus infinity, and limit of the function as x goes to negative infinity. Okay, now keeping these important points in mind, we can graph functions. For example, we want to analyze the graph of the function f of x equals 1 over x minus 1 over x squared. Now, in order to do so, we need, it's a good idea to find the domain first. We can write it here, the domain first. So it's a good idea to find the domain of the function at the beginning of the solution, or finding the graph or graphing the function. So the domain here is everything except the 0, because when x equals 0, the denominator is 0, and that means the function is undefined. That's singularity of the function. So from negative infinity to 0 union 0 to infinity, and since it's open at 0, that means 0 is not included. So this is the domain. Now the first thing we need to determine is the x-intercept and y-intercept. To find x-intercept, we set y equal to 0, and y represents f of x. So 0 equals 1 over x minus 1 over x squared. And then we bring this to left-hand side, it becomes positive. And then we cross multiply these, we get x equals x squared, and then bring this to the right hand side, it becomes negative, and we have 0. I brought this to the right hand side, or subtracted x from both sides, so we have x squared minus x equals 0. Then take x as a common factor, you get x times x minus 1 equal to 0. So we have x equals 0, x minus 1 equals 0, and from this we get x equals positive 1. So we have two x-intercepts at x equals 0 and x equals 1. Now we find the y-intercept. This is x-intercept. What is y-intercept? Y-intercept, that means we set x equals 0. But we know that if x equals 0, then the function is not defined. But this does not belong to the domain. Of the function of f of x. As you can see, the domain does not include 0 because it's open at 0. So we don't have y-intercept. Good. Now if we want to graph these things before we continue, so the graph so far looks like this. This is x-axis, this is y-axis. We determined the x-intercept. The x-intercepts are at x equals 0 and x equals 1. Then we determine the extrema. To determine the extrema, I mean maximum and minimum, we need to find the derivative, because these are applications of the first derivative. So the derivative of the function is, now the function is 1 over x minus 1 over x squared. So we can write it this way. X to negative 1, if we bring this up here, becomes x to the power negative 1. And bring this up here, it becomes x to negative 2. So derivative is negative x to negative 2 minus negative 2 times x negative 3. And then we simplify, we get negative 1 over x squared. Negative negative is positive 2, and then we bring x to negative 3 down, it becomes x to positive 3. Now this is the derivative. In order to proceed, we need to set this equal to 0, and the derivative does not exist or undefined. So alpha prime equal to 0, that means 0 equals negative 1 over x squared plus 2 over x cubed. And then we bring this to the left hand side, it becomes 1 over x squared positive equals 2 over x cubed. And then cross multiply these, you get x cubed equals 2x squared. Then bring this to the right hand side, it becomes negative. Then take x squared as a common factor, you get x minus 2 equals 0. And then you have x squared equals 0, that means x equals 0. X minus 2 equals 0, that means x equals 2. So we have 2 points, x equals 0 and x equals 2. They should be critical points, and actually stationary critical point, because the derivative is equal to 0. But we notice that this does not belong to the domain. So we exclude this and we take x equals 2 as a critical point. Now alpha prime of x is undefined when x equals 0, but this does not belong. We sometimes use this notation to mean does not belong to the domain. So we exclude this. So we only have x equals 2 as a critical point. And after that we study we make a sign chart of alpha prime, and we set x equals 2 here, and then we study the sign of alpha prime. But alpha prime is given by negative 1 over x squared plus 2 over x cubed. So we choose some values here. Let's choose a value greater than 2, like 3, and plug it into the alpha prime. Alpha prime of 3 is negative 1 over 9 plus 2 over 27, and then multiply this by 3, this by 3, to get a common denominator. You get negative 3 plus 2 over 27, and this is less than 0. So this is negative. Now we choose a value less than 2. Let's choose 1 and plug it into the derivative of the function. We get negative 1 over 1 plus 2 over 1, and that's negative 1 plus 2, which is greater than 0. So the function is increasing here and decreasing here. That means x equals 2. At x equals 2 we have a maximum point, relative max. And the point is 2 and f of 2. 2 and what is f of 2? We substitute 2 into the function, the original function here. Substitute 2, you get 1/2 minus 1/4, and that is 1/4. So 2 and 1/4 has an extreme value. So the graph becomes, our graph becomes, now we have 2 points, 0 here and 1 here. Those are the x-intercepts. And at 2 1/4, let's say this is 1/4, we have a maximum point. So we graph an arc. So this is maximum point. Good. Now the third thing we study is inflection point. So we need to determine inflection point, or the points of inflection. That means this is one of the applications of the second derivative. So we find the second derivative of the function. So let's find the second derivative of this formula, -x to -2 plus 2x to -3. It's easier to find the derivative of this than this. So this is -x to -2. Let's find the derivative of this. The derivative of this is negative times -2 plus 2x to -3 minus 6x to -4. So 2x to -3 minus 6x to -4. Okay, now we can rewrite this as a fraction. I mean 2 over x cubed. If we bring this down to get a positive power, and this down here, so we get 2 over x cubed minus 6 over x cubed. Now we set this equal to 0 in order to find points of inflection. So 2 over x cubed minus 6 over x to the 4th equals 0. And then bring this to the right hand side. You get 2 over x cubed equals 6 over x to the 4th. And since x does not okay, so let's cross multiply these. 2x to the 4th equals 6x cubed. And then we can divide by x cubed. Why? Because x cannot be 0. So we can safely divide by x cubed, because x is not equal to 0. 0 does not belong to the domain of the function. So we have, and here we can simplify. We have 2x equals 6, and that means x equals 6 over 2, which is 3. So x equals 3 should be an inflection point, but to make sure that it's an inflection point, we need to study the sign of f double prime at 3. Let's choose a value less than or greater than 3, like 4, and a value less than 3, like 1. If we substitute 4 into f double prime, we get a positive value. And if we substitute 1, we get a negative value. If we substitute here, then this is concave down. Here we are talking about concavity. The concavity is one of the applications of the second derivative. And here it's open. So as we can see, the function changes its concavity about the point x equals 3. That means x equals 3. At x equals 3, we have inflection point. The inflection point is 3 and f of 3. So 3 and what is f of 3? F of 3 is 1/3 minus 1 over 9. So multiply by 3, we get 2 over 9, 2/9. So at 3 2/9, we have point of inflection. And then actually the point of inflection is 3 and 2 over 9. So 3 and 2 over 9, we can extend. Let's do the graph again here. We have some points 0, 1, and 2. 2 has a maximum here. 2 with 1/4 is a maximum. And at 3, we have inflection point 3 and 2/9. Here we have inflection point. That means here it's concave down and then started to concave up here. Okay, now let's continue. And then we study the behavior at the singular point. Behavior at singular point. We have the singular point here is x equals 0. That means the point where the function is not defined. Okay, so this is a vertical asymptote, sometimes called vertical asymptote. So we study the limit or the behavior of the function around this. So we take limit as x goes to 0 from the right of the function, and this is limit of 1 over x minus 1 over x squared. X goes to 0 from the right. We get a common denominator. So this is x minus, by multiplying this by x, this becomes x minus 1 over x squared. The original function was 1 over x minus 1 over x squared. Okay, and then we can substitute the limit. Substitute 0, you get negative 1 over 0, which is negative infinity. So limit, when we substitute 0 from the right, we have negative in the numerator, and over 0, that's negative infinity. And if we take limit as x goes to 0 from the left of f of x, this is limit x minus 1 over x squared. X goes to 0 from the left. This gives us we should get negative sign here, because if we substitute a value that's very close to 0 from the left, it's negative. Let's say negative 0.5. Minus 1 is still negative, and when we substitute in the denominator, we get a very large number when we take reciprocal, so that's negative infinity as well. So around this point, let's continue on this graph. So around this point, we have around the singularity 0, the function goes to negative infinity from here and from here. Around 0 from the right goes to negative infinity, and from the left goes to negative infinity. Now the last thing to check is the end behavior. And that's what we call behavior at infinity. In this case, we take limit as x goes to positive infinity and limit as x goes to negative infinity of the function f of x. But what is the function f of x? The function f of x in this case is one over x minus 1 over x squared. X goes to infinity, and that means we have x minus 1 over x squared with limit x goes to infinity. If we substitute infinity, we get infinity over infinity, because infinity minus 1 is still infinity, over infinity squared is infinity. So we can apply, this is one of the forms of L'Hopital. This is L'Hopital form. because the L'Hopital forms are two: 0 over 0 or infinity over infinity. Those are called L'Hopital's forms. If one of these is satisfied, then we can just find the limit by just finding derivative of numerator and derivative of the denominator separately and substitute the value of the limit. So we have we need to find, here we apply L'Hopital's rule to get limit as x goes to infinity of what is the derivative of the numerator? It's 1. What is the derivative of the denominator? It's 2x, and substitute infinity. 1 over infinity is 0. And then we find the limit as x goes to negative infinity of the function f of x. This is limit of x minus 1 over x squared. And same thing, when we substitute negative infinity, we get something like negative infinity over infinity, and that's one of the forms of L'Hopital, because infinity over infinity or negative infinity over infinity, same, both are L'Hopital's forms. So we find the derivative in this case. L'Hopital's rule, we have limit of 1 over 2x, x goes to infinity, and this gives a negative infinity. This gives us negative, this gives us 0. So as x goes to infinity and x goes to negative infinity, the function approaches 0. That's the end behavior. Now we can graph the function or get some rough sketch of the function. This is x, this is y, and we had some points here: 0, 1, 2, and 3. 0 and 1 are x intercepts, and at 2 we have a maximum here. The maximum is 1/4. And we have at 3 we have inflection point at 2/9. So here we have inflection point. So we can connect the graph this way. And since as x goes to infinity, the function goes to 0, approaches 0, and then we need to intersect the x-axis at this point at x equals 1, and then the graph goes to negative infinity here as x approaches 0 from the right, and the graph goes to negative infinity around the 0 from this side. And as x goes to negative infinity, the graph goes to 0. So this is just a rough graph of the function. We determined some important points: the maximum, the point of inflection where the function changed its concavity. Here it was concave down, here it became concave up a little bit, and here we have x-intercept, and here this is a singularity at 0. So I should draw it as an open circle. So this is the graph of the function f of x. So we used what we learned and what the properties that we know, the features of function that we know, to graph a function. Let's do another example. The second example is easier than the first one because the first example included a singular point, but sometimes we have a simple function like f of x equals x squared plus 2x plus 1. And here actually you can graph this function without using calculus, but calculus can give us more information about, for example, information about concavity of the function, and intervals, and in behavior, intervals where the function is increasing, decreasing, things like that. And some of these properties, we already know them from college algebra, and some others come from calculus, that like the maximum point, the minimum point, and the inflection point, and so on. So for this function, let's first determine the domain. The domain is everything is allowed here, because this function doesn't have denominator, doesn't have roots, even roots, and these things that we worry about. So we don't want the function to be undefined. So this function is defined for all values of x. It's a polynomial. So let's find the x-intercept. What is x-intercept? We set y equals 0. So when y equals 0, we have x squared plus 2x plus 1, and then x plus 1 equals 0. That means x equals -1 repeated. So -1 and 0 is the x-intercept. Now what is y-intercept? For y-intercept, we set x equals 0, and that gives y equals x equals 0 to x equals 0 plus 1, y equals 1. So 0 and 1 is the y-intercept. So we have 2 points here, 0, 1, this point here, this is y-intercept, and -1, 0 is the x-intercept. Now then we find the extreme values. That means we need to find the first derivative of the function. The first derivative is 2x plus 2, and set this equal to 0. So we have 2x plus 2 equals 0. Bring this to the right hand side, you get 2x equals -2. Then divide both sides by 2. X equals -1. So now we study the sign of f prime around -1. So we choose a value greater than -1, like 0, and a value less than -1, like -2. When we substitute -1 into f prime, -1, 2 times -1 plus, 0, 2 times 0 plus 2, this is +2, so it's positive. Let's substitute -2, 2 times -2 plus 2, -4 plus 2 is less than 0. So the function is decreasing here and increasing here. That means the x equals, at x equals -1, we have f has a minimum point, relative minimum. So -1 and f of -1 is the minimum point. What is f of -1? We just substitute it here. -1 squared plus 2 to -1 plus 1. -1 squared is 1. Minus 2 plus 1, this is 0. So -1 and 0, this is the minimum point. And then we find points of inflection. If any exist. That means we find the second derivative of the function. Second derivative, that means we find the derivative of the first derivative, and that's +2. This cannot be equal to 0, so there is no points of inflection. Because if we study the sign of f prime, the second derivative, it's always positive, because the second derivative is +2. It's always concave up. It does not, so the function does not change its concavity. So f is always concave up. Now the fourth thing is the singularity behavior. actually we don't have singular points. These are polynomials. We don't have singular points. We don't have points where the function is not defined. 5. End behavior. For end behavior, we can find the limit as x goes to infinity of f of x, and that's limit as x goes to infinity of x squared plus 2x plus 1, and then we substitute infinity to get plus infinity, and we find x goes to negative infinity f of x, limit x goes to negative infinity, but we know that this is negative infinity. Positive, still positive infinity. X squared is the dominant term. So in either cases we have infinity, and actually from our experience in college algebra we know that if the leading coefficient is the coefficient of x squared is positive, then it's concave up. So that means the end behavior, this is the end behavior, and this is the end behavior here. Both of them go to infinity. So this is how we can determine the end behavior for polynomials. So here we can graph the function. This is x, this is y. We need to determine first the x-intercept and the y-intercept. We have x-intercept at x equals -1 and y-intercept at y equals 1. So these are the intercepts, and then we have extreme value at -1, 0. -1, 0, minimum point. That means the graph looks like this at this point. It's minimum, smallest value. And we have, what about the end behavior? So this graph, we don't have, it's concave up, always concave up, and it's always concave up from here. And as we can see, the end behavior of the function, as x goes to infinity, what happens to the graph goes to infinity. As x goes to negative infinity, the graph goes to plus infinity. So this is the graph of x, and this agrees with what we know